if we think of having like an x and a y-axis here, like this x-axis, this x-axis is the y-axis. Right here, this would be where 0 degrees would be. And then as you go around in the counterclockwise direction, the angles would get bigger, right? So here, this would just be 28 degrees. But when we find those angles, we do that in the counterclockwise direction. So right here, if we think about there being an x and a y-axis here, right here would be 0 degrees. Excuse me. So there are two options you can give me for this answer, for the direction. It either, because it's going, this 110 is going in this direction, which is the opposite direction, right? We're going clockwise. We can either say it's negative 110 degrees, because it's going from 0 going in the clockwise direction. Or we could think of it, in this direction. How could I figure out what that angle right there would be? What? 360 minus 110, which will give us 250 degrees. So on that one, it's okay with me if you've got negative 110 as your angle, or 250. Probably because I did not explain that really so much in the video a lot. You may have just had 110. But it either needs to be negative 110 or you could do 250 degrees. So knowing that, look at number 3 and look at your angle for that one. And see what you could get for that. Okay, so for number 3, what is my angle? Either negative 70 or, what did you say? 290 degrees. Either one of those would be appropriate to put. Okay, and of course the magnitude is 12 there. Okay, questions? All right, let's look at this resultant vector for this one. I'm going to use parallelogram method just because I find students tend to do a little bit better with that. So the way these are drawn right here, I need to make a parallelogram. Okay, a parallelogram is only a rectangle if you have a right angle. We don't have a right angle here. So I'm just going to take and draw a line parallel to the other side, right? So this side right here, I'm drawing a line parallel to it. And then over here, I need a line that's parallel to this side right here. So that would look like this. Something like that. It's not perfect, but decent. So the resultant vector is going to go from that common endpoint right here across to the other corner of the parallelogram. So that would be my resultant vector. Yes? Do 360, which would be a whole entire rotation all the way around, and subtract 70, which would give you 290. So you're either going backwards 70, which would be negative 70, or you could go all the way around this way, 290 degrees. Yes. Yeah, if it's below that y, if it's below the x-axis, you are either going to give a negative angle or you could subtract it. Because on all of these, it's like this horizontal right here, that's your 0 degrees. That's where you're starting from. If it's given like this. All right, try 5 and 6. Let's see what those look like there. The only thing wrong about it is you do need an arrow, so you need a dot. And really, these worksheet doesn't put dots right there, but I think the dots are the point and the arrow. Yeah, your idea is pretty good. Maybe a little, not perfect, but pretty close. Alright, that's looking pretty good. I think you guys have the idea. So on 5, you should have, let's see. So on 5, you should have something that looks something like this. Do make sure that you put a dot right here. This worksheet does not put dots. It only puts the arrows, but I really want to see the dot on the end as well. And then the arrow has to be on the other end here for this one here. We're going to have something like this. Mine's not perfect there, but something like this. Okay, questions? Okay. All right, let's get out those notes that you guys started yesterday with that video. Yes. Okay. If you have a problem where, like, for example, well, let's look down here. If we look at, let's get rid of that. No, not right there. Let's see. I think it's down here. So, sometimes. So, like, if you have a problem, like, for example, here, which I was given ones that were on number 1 from the worksheet. If you're given a problem that doesn't really have any context, so it just tells you magnitude and direction, it is usually going to be, like, for this particular one, you had a 90-degree vector, so 0 degrees would be right here. Going in this direction, 90 degrees would be right here, so the vector would look like this. And then whenever it tells you that the other vector has a direction of 180, that means you're going all the way around here, 180. We're going to see some today where they're not 90, 180, 270, where they're not on those lines. So it might be we have an angle of 115, or we might have an angle of negative 60. So we'll see some of those. We'll do some where you'll see what that looks like. Okay. All right, we did the first 4, I believe, on that video. Is that right? First 4 examples. And then so example 5 is what we're going to pick up. Okay, so winds are certainly a big application of vectors. Really, honestly, this is just a tiny piece, teeny piece of physics. But if you take physics in college or here, although I don't think we had it this year, but if you take physics, lots of it is vectors. A huge amount of it is vectors. So it's all very math-based, but it is used a lot for, vectors are used a lot for basically any type of force. In fact, last year, a couple years ago, some of my students said they were taking, I can't remember the name of the course, but it was a School of Math and Science class, and it was like biomedical technology or something like that. And they already knew how to do vectors because in their class they had used vectors to kind of like examine the different forces on a hip, like whenever you have a hip replacement. So there's all kinds of places in physics, both applicational, like in medical technology, and just in like theoretical sort of things where you're going to see vectors come up. They are used a lot in those sort of aspects. So this is just like a really quick overview. If you were to take physics, then it would be in depth of what you would be doing. Wind is blowing at 45 miles per hour. The wind is blowing in a direction 30 degrees south of west. Find the westward and southward components of the wind. So, in this case, we're going to think north, south, west, east. And my wind is blowing 45 miles per hour in a direction 30 degrees south of west. So, excuse me, south of west. West is our main direction. We're going to the south of it 30 degrees. So we would draw it like this. So on these types of problems, you're not going to ever really have an angle bigger than 90 degrees, and you're going to use the north, south, east, and west to figure out where it's going to be at. And so what the question is asking us to find the westward and the southward components. So I'm going to use red for this one. The westward component would be like this, and the southward component would look like this, and then it could make, a parallelogram there. So this question, I don't think, it's hard when I do videos because I can't remember what I did in the video as well. I don't think that you've done one of these before. This one actually gives you the resultant vector, and what we're trying to figure out are the westward and the southward components. So I'm going to call this W, and I'm going to call this one S, even though S is a terrible variable because it looks too much like a 5, to remind myself that this is westward and southward. So, obviously, whatever S is here, this would also be S. So, I want to know how much of this wind is blowing to the south, how much of it is blowing to the west. This would be important, like, perhaps you maybe have like a building here, and as the wind hits the wall of that building, if it's facing east, the only wind that's actually going to really push on that wall here is the westward wind. The southward component, doesn't affect it really there. So, here we would have if we're looking for, let's say we're looking for S first. So if we're trying to find S, I do know this side right here is 45 degrees. So if I'm looking at S and 45, which one should I use? Sine, cosine, or tangent? $30 is the angle that I know, right? So, what? No. So if 30 is the angle that I know, is this opposite, adjacent, or hypotenuse? It is opposite. And what's this? I shouldn't have a degree sign right there. It's 45. It's not supposed to be degrees at all. It's 45 miles per hour, so it's a length right there. So for the 45, that is my hypotenuse, because the right angle is right here. Or if you're looking at the bottom triangle, it's right here. But either way, this is the hypotenuse right here. So opposite and hypotenuse is going to be sine. So I'm going to say sine sine of the angle, sine of 30, equals the opposite, which is S, over the hypotenuse, which is 45. So we're going to multiply both sides by 45 here, and S is going to be, let's get the calculator out. Make sure we're in degree mode. 45 sine 30. And we're at 22.5. If I want to find westward component instead, so instead of finding this, or at this point, you could, if you wanted, since that's a right triangle, what could you use without doing any trig? We could use Pythagorean Theorem. So we could use Pythagorean Theorem on this one. Or, if we wanted to do trig, if we're looking for the west side, that is our adjacent over hypotenuse. So that would be cosine. So we would set it up cosine of 30 degrees equals the west over 45. So we'd have 45 cosine of 30. And that's going to give us 38.971. And these would be in miles per hour. It is okay with me here because I used a S and a W. It's okay if you just leave your answers like this. If you don't use S and W, if you call it like an X and a Y, please tell me that this is the southward component and this is the westward component. If you use an S and a W, I will assume that's what you mean by that. Okay, questions? Yes, so like if we broke this down, okay. You won't need many sheets for that one, will you? All right, so for like what we have found here is like if we have a wind in that direction at 45 miles per hour, that means that the westward component is 38.971. So anything like it's hitting with that force, anything that's westward, and then the downward or the south component is 22.5 right there. So it's like you're breaking that apart into its perpendicular pieces. There's actually a method that you can use that I'm not going to teach you because I'm going to teach you the law of sines and cosines way here in a minute, or just I'm teaching you the trig way to do vectors. There are a lot of different ways to do vectors, but this is in the trig unit, and so we're going to do the trig way to do vectors. Other ways to do vectors still involve trig, but they're a little bit different than the way I show you. So. All right, I like this problem. A sled is being pulled with a string. The string makes a 62-degree angle with the ground. The person pulling the sled is exerting a force of 4 newtons. What are the horizontal and vertical components of the force? So, if you think about what is going to happen if you have a sled, and it's so cold today, you just about need one. Hold on, what's happening? Why is it freezing? let's try opening this back up. Maybe I'll have to restart the computer. Maybe. Okay, so sled is being pulled with a string. The string makes a 62-degree angle with the ground. So what we've got here is we're going to have, here's our ground. And so if you have a sled, so here is our sled. And there's usually going to be a rope attached to this sled. And there's a person with a tiny head who is going to pull this rope, right? So whenever you pull on that rope, you're exerting a force, they tell us, of 4 newtons. The abbreviation for newtons is just capital N. It is a unit of work that we're doing here. So it's a force that is being measured. And so whenever you do that, your force is exerting a horizontal force and a vertical force. Right? Basically, all of that vertical force is wasted. It would be most efficient here, because what you want to happen is you want the sled just to be pulled along the flat ground, right? Now, if this was a slant, if this was on a hill, it would make a difference. So we're considering this flat ground right here. I should put that in the problem. But ideally, you would only pull the sled forward, right? You don't need to pull it up. Because when you're pulling up on that sled, it's either just going to pick the front of it up or it's going to do nothing because the weight of the sled is just going to, it's not going to be strong enough to pull the front of the sled up. However, to pull the sled at a perfectly horizontal, you would have to get down on your hands and knees and pull the sled along the ground, which would not be most convenient, right? So whenever we pull the sled, we generally are going to pull it at some sort of angle like this. So what we want to know is what are the horizontal and vertical components of the force. So basically, how much of our force are we wasting and how much of it is actually being used to pull the sled. So this is 62 degrees right here. It's not drawn to scale very well, obviously, in this case. And so I'm going to call this right here H because it's my horizontal force, and I'm going to call this V for vertical. And horizontal and vertical obviously make a right angle to each other. So this is similar to the last problem we just did, although it's a different application of that problem, right? So if we want to find, let's go for H first. H would be my adjacent side, 4 is my hypotenuse. So I would say cosine of 62 degrees is going to equal H over 4. So I'd have to multiply both sides by 4, and then 4 cosine 62 is going to be 1.879. And this is measured in newtons. So 1.879 newtons of our force is being used in the horizontal direction. If we want to find the vertical direction, how am I going to set that up? We're going to use sine. So it's basically the same problem, but this time it's going to be sine of 62 degrees. And instead of H, we're going to use V over 4. And so if we multiply both sides by 4 here, for sine 62 is going to give us 3.532. So our vertical component is 3.532 newtons. So if you were wanting to improve the efficiency of what you were doing here, if you held that string at a lower angle, so maybe instead of 62 you had 42 degrees, which is actually probably closer to what I actually drew, right? Then you would be pulling the sled at a more efficient angle because less of your force would be wasted. And this stick figure's pulling the sled like this anyway, which is kind of odd. So he could just lower his arm there. Yes.
So you used the triangle up there, right?
Yes.
So could you use the?
You could use parallelogram, and so if you did that, this green vector right here would look like this. They would have the same, and then so your parallelogram would look like this. And then so the resultant is like the one they gave you this time, so it's from here to here. So yes, you could use that. Also, the triangle method is basically just like half of the parallelogram method. So they're equivalent to each other. You can always use either one. There's some cases where it just makes more sense to me to use one instead of the other. Sorry. But you may always choose to use one instead of the other. Okay, questions? Okay, so let's start doing some that are not right angles. Okay, because everything you've done so far had a right angle in the triangle. So this is what I sometimes call just a naked problem. It's not got any context. It's just telling us we've got vector A has a magnitude of 3 centimeters and a direction of 0. Vector B has a magnitude of 4 centimeters and a direction of 50. Find the magnitude and direction of vector A plus vector B. So if we think this one does not have north, south, east, or west, so it's like we're starting from like a coordinate plane with an x-axis and a y-axis. And on that coordinate plane, as we saw earlier, this x-axis right here, this is like 0 degrees whenever you're thinking about angles. So vector A has a magnitude of 3 centimeters and a direction of 0. And one thing I'm going to do here that I suggest, I'm not going to pass it out just for the notes right here. I'm going to let you just kind of follow my lead on this. But whenever we get to the ones that are a little bit more complicated, I do suggest actually drawing these to scale. So I'm going to pull up this ruler. And the protractor. Alright, so, and you may have to sort of scale it, because this one's pretty easy because it says centimeters, so we can actually probably fit this on here. So we have a direction of 0 degrees and a magnitude of 3 centimeters. So when we draw this vector here, you guys just kind of draw one that looks like what I've got. I'll give you the rulers and stuff here in a minute. But we'll use blue for this one. We got a vector that's in 0 degree direction and it has a 3 centimeter length. Then we also want to draw a vector. We're going to line up our protractor right there on the x and y axis. I'm going to put myself a little dot at 50 degrees. Notice right here that I said this is 0 degrees. On your protractor, there's 2 numbers, but 0 degrees is right here. So I'm using the inside set of numbers here. So I got 1, 2, 3, 4, 5. There's 50. So about right here, I'm going to put myself a little dot. Okay, and I'll give you guys one of these so you can follow along here in a moment. Alright, so this is kind of hard to do on the, it's easier to do on paper with the ruler. So I'll line this up here, and I'm supposed to have a magnitude of 4. So this vector, which I'm doing green, is going to have a magnitude of 4. So it will look like this. And so this angle right here is 50 degrees. And so what I've got to do now is I want to draw in some dotted lines that make this a parallelogram. So it'd be a line like this, and then a line pretty much like that. I think that's pretty close right there. Whenever, I guess you could use your ruler to make sure it's a little bit, well, that's pretty good, close there. Alright, now before I draw in my resultant, I want to think of a couple things because the angles are going to be a little tricky on this. A parallelogram. What do I know about opposite angles in a parallelogram? They're equal to each other. So that means this angle right here is 50 degrees, right? So these two angles have to be equal to each other. So what are they going to be? It's going to be 130. How'd you get that, Wesley? Okay, 180 minus 50 will work because in a quadrilateral, your angle should add up to 360 because it's like two triangles put together. But that means half of it should add up to 180, right? So this is going to add up to 130 degrees here. You'd have 130 here. I like drawing those in before I draw my resultant vector because sometimes once the resultant vector is there, it's hard to see because we will need at least one of those angles there. And so resultant vector is going to go from the common endpoint here to the opposite corner over here. Okay, questions on our picture? All right, so my direction of this angle is this angle right here, right? Because that red, let me make it a little bit darker right there so we're certain that that is the, all right, so this is what we're looking for, right? So the angle would be whatever angle this is right here. I'm going to call it theta. You can call it x. You can call it whatever you want to call it. And then I also need the magnitude, which is the length of that red vector there. And I didn't label it, but this was 4 centimeters, and this was 3 centimeters. So this should start to help us see why this is in this section, because can I use Pythagorean Theorem or regular trig to find either one of those? I cannot because I don't have a right triangle. So I can use the law of sines or cosines here. What am I going to have to do first? We are looking for either the angle or the magnitude. We need to find them both. There's one we're going to have to find first. What do you think? Good. So if this right here is 4, it also has to be 4 centimeters here. We cannot, because this is not a right triangle. So since it's not a right triangle, we can't use Pythagorean theorem. So cosines is what we're going to have to use here. So law of cosines is going to tell us that x squared is going to equal 3 squared plus 4 squared minus 2 times 3 times 4 cosine of 130. That's the measure of this angle right here. And I figured that out when I drew my parallelogram. The angles that are across from each other are equal to each other. And then the angles that are beside of each other should add up to 180. Okay? So we got 9 plus 16 minus 2 times 3 times 4 cosine of 130 is going to give us 40.427. Well, that's not our final answer. We got to square root both sides, so don't change this right here. All right, so we get 6.358. So we have just found that this side is 6.358. Okay, so that is our magnitude. And I guess it's centimeters. So this is part of our answer. The other part that we need is the direction, which is this angle right here. How could I find it? Matthew? Good. Alright, I'm going to use that theta since I labeled it that here, but you can call it whatever. Alright, so 6.358. It will be better if we save that number in our calculator there, or just, I think we'll be able to get by with just the answer. So we got 6.358 sine of theta equals 4 sine of 130. We'll divide by 6.358. So 4 sine 130 divided by, let's do second answer. So sine of theta is 0.4819 and so on. We will do sine inverse, and so theta is going to be 28.811 degrees. This is our direction. So that's the other piece of our answer. A lot of times, especially like whenever we test on this, I'll only ask you for one, the magnitude or the direction, just because it's hard to do answer choices where you're putting them both there. And that looks about right, because this was a 50-degree angle. 28 would be a little more than half of that, so that looks about right. The good thing about drawing them to scale is that you can see if it looks like it makes sense whenever you look at your answer. In fact, you could go up here. Now, this is not the perfect way to do it because we are not perfect at measuring. But if I go up here, it looks awfully close to 28 degrees if I measure it with a protractor. So if you draw it to scale, you can also measure it to see if it looks right. Which we could do for all problems, but generally for the ones that make right angles, I don't spend the time to draw those by hand. 2 scale. Okay, questions on that one? All right, let's try one more of these. All right, so an airplane is flying due west at a velocity of 120 meters per second. The wind is blowing 20 degrees north of west at 15 meters per second. What is the magnitude and direction of the plane's resultant velocity? So, let's see, we're going west and then north of west. So we really need, we need more room over here to the side. Okay, so whenever you are doing these problems, especially like in this particular case, drawing this to scale, you can't really draw like something that's 120, right? It's going to be too big. So if we're going to try to draw it to scale 120, we might want to let 120, we might want to let maybe like 20 meters equals 1 centimeter on our ruler. So that means 120, I guess it's 120 meters per second would be just 6 centimeters. Because I would just divide by 20. What would 15 meters per second be? I'm trying to draw this to scale. What? So if this is our, we're saying 20 meters per second is 1 centimeter. So for 120, I'd change it to 6 by dividing by 20 there. So here I could divide by 20 and I'll get 0.75 centimeters. So when I draw it, that way it'll still be to scale. Because sometimes these don't fit. And so for 6 centimeters west, our vector will look like this. We use blue. Then to do our angle, we want to go 20 degrees north of west. So if I take my protractor and I line it up right here, I want to go to the north side of west. West is my main direction. I'm going to the north 20. So like right here, because that 0 right there is on the westward component, which I'm looking at, I'm going to use those outside numbers this time, and I'm going to put me a dot right here at 20 degrees. And then I will take this and try to line it up. So I'm going to do it this way. No, neither one of these work that well. Let's do best we can. It's easier when you have a real ruler. This digital ruler is not the most helpful. Too much. Still not right. Okay, still wrong. Alright, we're going to call this right here close enough. It's easier whenever you have a regular ruler. And so we need it to go in this direction, but it's only going to be 0.75. The length is only going to be 0.75. So if we do that here, I realize my angle's a little off. If we draw this vector, I'm going to use green here. 0.75 is just going to look about like this. It's going to be a little teeny tiny vector. So to do a parallelogram here, we'll use a dotted line. We'll do this first. Have a horizontal line here. And I've got to have a slanted line here that I think looks something like this. Now, I like to do my angles before I draw in my resultant vector. So right here, this little angle right here is 20 degrees. And then, if this is 20 degrees, what is the measure of this big angle over here? It is going to be 160. And so, to draw in the resultant vector, you're always going to go from the common endpoint, which is right here, to the opposite corner, which is over here, and not even going to let me quite draw it in perfectly, because it's such a skinny triangle. So I need to label my sides here. This is 15. This is 120, which means that this side over here would also be 15 there. It's drawing crazy stuff now. So if we're trying to find that resultant vector there, we would have to use our law of cosine. So we would say x squared would equal 15 squared plus 120 squared minus 2 times 15 times 120 cosine of 160. And we get x squared is 11,025. And we can square root both sides. We're going to get, is that supposed to be perfect? Oh, no, I didn't put cosine, did I? Let me try that again. Alright, let me put cosine of 160 here. Okay, ignore that I wrote that down. That's not right. We're going to take the square root of this. It's going to give us 134.193. Now, and this is meters per second because that's how we were labeling magnitude. So that's our magnitude right there. If I want to know the direction, which direction, just tell me in general. Is it north of west, west of north, south of east, east of south? What have I got? It is north of west, right? And so my angle, it's kind of hard to do on these, but my angle is this teeny tiny little angle right here. I'm going to call it theta. And so it is across from the 15. So I would say sine of theta over 15 is going to equal sine. The only other angle I know in this triangle is this 160, although I guess I could find this other angle here. But is not necessarily helpful. Over the side that I know here, which is the 134.19349.425. So we'll cross multiply 134.193 sine theta equals 15 sine 160. I divide by the 134.193. So sine of theta equal 15 sine 160 divided by 34. So I got 0.0382, and I'll do inverse sine, and I get 2.191 degrees, and that would be north of west. And that looks about accurate. It should be a teetony angle right there. Definitely less than 20 degrees. You can see how this would be really important if you're flying an airplane, because it has increased the speed, because this is more or less a tailwind, right? It's mostly going in the same direction that you're going. But it's also throwing you 2 degrees off course. So 2 degrees off course does not sound like a lot, but if you're traveling thousands of, hundreds or thousands of miles, 2 degrees off course is a big deal, right? So now I do realize planes these days, if we're talking commercial airlines, are probably mostly flown by computers. Pilots are there in case the computers mess up. And probably some landing and takeoff sort of things, but somebody had to program those computers. Also, if you are, just like flying a small plane, probably may not have some of these instruments, although I'm not very familiar with that, because small planes scare me, and I don't know if I want to get in one or not, but they're probably still safer than around the car, but here. Questions? We got one more quick one that is actually not going to take us very long. Okay. There's one more instance that I want you to see that happens sometimes that is going to be really easy to solve once we realize what is happening. So I am going to draw this out. I have a magnitude of 3 feet in direction of 20 degrees, and I'm going to get that. If it's still saved, yeah. Okay, good. That ruler and protractor back out here. So I've got 20 degrees. 20 degrees. I'm going to put me a little dot right here at 20. And a magnitude of 3. And I'll tell you what I'm going to do here. I'm going to decrease the size of my ruler so that I can fit this on this page. So that's more. It's so hard to do this on the computer. Okay. So this is more or less right. I've got a direction of 20, a magnitude of 3. So I have this direction here. Then, my other one has a direction of 200 degrees and a magnitude of